Hi everyone. Today we'll be discussing Monte Carlo methods. Why are we discussing Monte Carlo methods? Well, we've just sort of finished describing Bayesian methods and introducing posteriors. And a large part of what we do when we have posteriors or any kind of complex probability distribution is that we draw samples from them. Oftentimes these are very high dimensional distributions, so it isn't clear where the bulk of the density lies with respect to various parameters on which, or various variables on which they depend. So drawing samples is a natural way to do this. So let's start. And let's highlight the fact that Monte Carlo methods as well are used for much more than sampling. They are used for sort of integration, or equivalently performing sums. They are used in optimization, and sampling of distributions, amongst multiple other tasks that Monte Carlo is used for. So before we sort of delve into how it's used in sampling, let's say a word or two regarding how it's used in integration. So suppose that I have the following integral to take. So I'm taking an expectation value that's on the left-hand side as some function g of r with respect to some pi of r. Pi of r will be some kind of distribution, and g of r is, well, some function of r. And the notion is that I do not know how to compute this integral analytically. So I start off from this point and I ask, can I use something that we've previously been introduced to in prior chapters in order to be able to perform this integral? Now suppose, and this is an important supposition, that I know how to sample r from this distribution. Maybe this distribution lends itself to sort of the inverse CDF method, or maybe it's a Gaussian I can use Box-Mueller, or it's one of those distributions that I can sort of analytically sample from. Now, if that's the case, then this integral can be approximated as a sum from j is equal to 1 to big J. I'm going to divide this here by big J, so it's going to be something like an average of g of r sub j, given that r sub j is drawn from pi. So the idea is to draw many different samples from the distribution from which I can draw samples analytically, evaluate g at those points, and then take the average with respect to the number of samples, and take the average, with respect to the number of samples. So this all relies, of course, on me being able to do this, which is a big if. Now let's up it up a notch, and suppose that I don't know how to sample directly from pi. What happens then? So let's go back and think of an integral like this, where the assumption now is that I do not know how to sample from pi analytically. Maybe it doesn't lend itself, like we said, to an inverse CDF method, or maybe it isn't sort of a simple function, like an exponential distribution, a normal distribution, something like that. There is something I can do. And perhaps, while I may not be able to sample from pi, I may be able to sample from h, some other distribution. Now I have to make sure that the distribution h has the same support as the distribution pi. In other words, if h is a distribution from 0 to infinity, then pi also needs to be a distribution from 0 to infinity. Or if pi is from negative infinity to infinity, then h should also have a support from negative infinity to infinity. There are a couple of caveats to that, but for now we have kind of a high-level discussion. If that's the case, and I know how to sample from h, then kind of using the logic that I previously introduced, maybe I can write something of this type as my approximation to the integral. This is an approximation. Now, of course, in the limit that j goes to infinity, then perhaps I can eventually obtain an exact result. Okay. What if I'm not taking the average of anything? What if I'm just performing an integral like this? What do I do then? Well, something very similar to what we've just talked about earlier. Perhaps I can divide and multiply by the same probability distribution. In other words, multiply by 1 and approximate the following integral as 1 over j, sum over j from 1 to j, of g of rj divided by pi of rj, assuming that rj is drawn from pi. Previously, I should have said assuming that rj sampled from h in the previous slide, but it doesn't really matter. So we can start asking ourselves the question, okay, well, how do I pick the pi that I need? I know that the pi should have the same support as g of r. I mean, in some sense, if pi is from 0 to infinity, right, and g of r is from negative infinity to infinity, then I will never draw samples which are negative. And if I never draw samples which are negative, then I really won't be approximating this integral. So it's clear that pi of r needs to have the same support as g of r. But beyond that, what other conditions are there on pi of r? And the reason I'm mentioning this is because, Monte Carlo at some level is as much of an art as it is a science. Sort of efficient Monte Carlo requires some degree of insight regarding the task that you are to perform, whether it be an integration task or a sampling task. So take, for example, a g of r that looks something like this. That's the integral of the function that I want to, or that's the function that I'd like to integrate, whose area I'd like to determine. Okay, it doesn't quite look analytical. It's kind of a lopsided double Gaussian. So, it doesn't look analytical. And suppose that the pi of r that I select is the following. And yeah, it has support all the way out here. And this also has g of r exists all the way out here. But, this here's my pi of r. Now, let's suppose that I draw a sample from pi of r. Okay, so, I can draw samples from pi of r analytically. So pi of r is a Gaussian. I draw a sample, and it's going to be maybe here. Great. Now, calculate sort of g of r evaluated at this value. Well, essentially, g of r at this point is 0. Okay, so the first term in the sum is 0. Now, let's try to draw another sample from pi of r. Well, maybe it's going to be an even more probable sample. It'll be here. What's the value of g of r here? Well, it's going to be another 0. So the problem is that I can keep sampling and sampling and sampling, and I will never sample samples in the general region where g of r has substantial density if my pi of r is totally off-centered. On the other hand, if my pi of r was a Gaussian, roughly centered at g of r, then the sum would converge much, much more quickly. Now, this example that I gave here is an extremely simple example in one dimension. On the other hand, when you're starting to think about multidimensional sampling problems or multidimensional integration problems, developing a pi of r which is ideally, convenient to sample from and sort of drawn or centered at roughly the region where g of r has most of its density starts becoming extremely important. So at this point, sort of physical intuition has to start kicking in terms of what pi of r we are to select. What I've described so far is really sort of Monte Carlo methods. Now, as part of this chapter, we'll also be introducing Markov chain Monte Carlo methods. Markov chain Monte Carlo methods are, in some sense, if you can think of them, adaptive. We're not just drawing samples from some pi of r, but we're eventually sort of drawing samples from some pi of r which may be centered potentially at different regions starting to approach the g of r. So far, as we were drawing samples from the pi, each one of our samples was completely independent of one another, and they were used to evaluate sort of the g of r at the sample location. In methods that we will introduce shortly, which are kind of a specialization Markov chain Monte Carlo, the samples will not be independent and in fact will be correlated, and they will form what's called a Markov chain, which we'll describe shortly. But for now, let's give sort of the simple example of Monte Carlo for an example that we've seen already, the conjugate normal gamma model. So let's start by saying that tau is drawn from a gamma distribution. Tau here is going to be the precision. The mean, given the precision, is drawn from a normal distribution, and its hyperparameters are xi, and there's a psi naught multiplied by tau. So together these form the variance. And then I have a likelihood for my IID data, which is going to be simple. It's going to be drawn from a normal distribution with some mean mu and a variance of 1 over tau, tau again being the precision. So this here is my likelihood. This here is my prior. Perhaps my goal at this point is to draw samples of my posterior. This is my posterior, which is obtained by multiplying my likelihood, which is proportional to my likelihood multiplied by my priors. What I'm not including, as usual, is the evidence, the probability of the data, which does not depend on mu and tau. Okay, so if my goal is to draw samples from this posterior, how do I do it? Well, this example is cooked up a little bit, and if you multiply these three out, being careful again, by three I mean the two priors, and if you have n data points, maybe I should say these 2 plus n probability distributions, you will obtain a posterior from which you can draw analytical samples. But as an exercise, let's suppose that our goal is to do some kind of Monte Carlo. So one type of Monte Carlo is ancestral sampling. Now, if we remember ancestral sampling from chapter 1, let's try to just remember for just 1 second. The goal is basically to say, I can decompose this as the probability of w, 1 to n, multiplied by the probability of mu given tau, w1 to n. That's true. That follows from the sort of the rules of multiplication of probability. But if this is true, this suggests that I can first draw tau from this p. I'm going to use sort of slightly inappropriate notation, but I'm going to call it p of tau conditioned on w1 to n. Normally we don't put the random variable in the distribution, but let's go ahead and do that just for simplicity, for notational simplicity here. And then I'm going to draw mu from the following distribution. So this is a type of Monte Carlo called ancestral sampling. I have a joint distribution to sample from. I will first draw samples of tau, then I will draw samples of mu given tau. And I know that that works because if I multiply the two, then I obtain the joint, these two densities, and I get the posterior. Great. So now you're going to ask me, okay, well, what is this distribution and what is that distribution? How do I obtain those? Okay, well, for that, let's start with this distribution here. In some sense, we can call this distribution a marginal over tau, and this is another marginal over mu. So the question is, how can we derive these two different marginals to sample from. It turns out we'll be able to do it because this example is pretty simple. Ancestral sampling will not in general work for multidimensional distributions. We'll have to use something a little bit more advanced and a specific type of Markov chain Monte Carlo called Gibbs sampling. But we're not there yet. Right now we're trying to do direct Monte Carlo. We draw direct samples from these distributions, and the samples are decorrelated at every draw. So the idea here is to draw a sample at every iteration, some mu j, tau j, and then eventually to collect all of these samples. And then if I like, I can perhaps plot them, right? So I can histogram them, for example, the mu samples, or I can histogram the tau samples if I like, and so on and so forth. I can even compute things like mu squared average by sort of taking my mu j samples, squaring them, and making sure to divide through by j, summing over j. So there's all kinds of different things that I can do once I have samples of mu and tau. But again, goal number one, in order to obtain samples of mu and tau, is to obtain this distribution and that distribution. So obtaining p of tau given w1 to n. How am I going to do that? Okay, well, let's start with p of mu given tau w1 to n, which I know how to construct. That's going to be p of w1 to n given tau and mu. That's the product of all of my Gaussians. That's my likelihood. Multiplied here by p of mu given tau and p of tau. Right? Those are my priors. And of course, divided by the probability of the data. Now, so in other words, I know how to calculate this object. What I also know is that p of tau given wn is the marginal of that object. So if I marginalize over mu of my posterior, then I should obtain my marginal over tau. Okay, how do I do this integral? Well, let's think for a second. This is really the integral. And let's pull the stuff that does not depend on mu out of the integral because I don't care about it. It's not being affected by the integration operation. I have p of w 1 to n tau mu p of mu given tau. Well, this is a Gaussian. That's a Gaussian. The product of the two of them, if I expand the argument of the exponential and recomplete the squares, I can rewrite as a Gaussian in mu. If that's the case, I know how to do a Gaussian integral. So in some sense, I'm done. I'm one Gaussian integral away from obtaining p of tau. And if I were to do the math correctly, then I find that p of tau given w 1 to n is going to be a gamma distribution. The random variable is tau, alpha plus n over 2, and the other term is 1 over beta plus 1/2 n s bar, which I'll have to define in a second, psi naught over psi naught plus n w bar minus xi, close bracket, and s bar here is 1 over n, sum over n, wn minus n bar, wn minus w bar, and w bar is 1 over n, sum over n wn. Again, when I don't make very explicit the limits, it's because I'm integrating over everything. So there we go. I mean, it's complicated looking, but in the end, this result came from the product of two Gaussians. expanding, recompleting the squares, and integrating over mu. So parameters are going to recombine in order to give you something that looks like this. So we've just obtained the expression or the distribution from which we will sample tau. That expression is a gamma distribution, and I know that I can sample from gamma distributions directly using the inverse CDF methods. In fact, most tools, such as Python, have direct ways of sampling from gamma distributions without you having to code up the CDF from scratch through, by importing the right libraries. What about P of mu? Given tau and W1 to n. Okay, well, once more, we know that P of mu, we know that P of mu and tau is obtained from P of mu given tau W1 to n multiplied by P of tau. So that implies that P of mu and tau given Wn divided by P of tau is equal to P of mu given tau W1 to n. Well, that's interesting. That doesn't even involve an integration at this point, because I know what this is. That was just my likelihood, W1 to n given mu and tau times P of mu given tau times P of tau divided by my evidence, if I care to keep track of it, divided by P of tau, which is P of mu given tau W1 to n. So I know how to take the product of these two, this prior and this likelihood. What is this prior? It's a Gaussian. What is that prior? It's another Gaussian. The product of the two, once I recombine them, once I, again, multiply them together, expand the exponentials, recomplete the squares to make it look like a Gaussian in mu, is going to look like a Gaussian in mu. This term here doesn't depend on mu, so it's just going to be a normalization that I can figure out later if I want to. So what I'm advertising is that this is a very simple, obtained by sort of algebraic manipulation. And it will be a Gaussian. So let's go ahead and write it out explicitly just for posterity, but it's going to be a normal in mu. And then the mean, again, obtained by this algebra. It'll be complicated, but in the end it'll look complicated, but in the end it's just algebra. Is this. And the variance is this. So that's the mean of my Gaussian, and this here is the variance. And we're done. So now that we have P of tau given the data and P of mu given tau in the data, then we can start drawing samples of mu and tau. So, we have tau given P of tau and the data, and we have mu of tau. We know this, we know that. We draw one sample for tau, one sample for mu. Then after the next iteration, we can choose to draw another sample. Should be tau. All the way up to, big J, which in the end will give us, as we said, big J samples of mu and tau. This is a Monte Carlo method. All of our samples are independent. Each iteration is completely independent of every other iteration. And then what do we do? Okay, well, maybe, what do I do with my samples? At some level, that's up to me. I can compute the mean of mu. That'll be 1 over j, sum over j, mu j. I can compute the variance of mu if I want. That's going to be 1 over j sum over j mu j squared minus sum over j, minus j all this squared, bracket, bracket. So that's the variance. But I can also compute things that, may be very difficult to compute analytically, such as various functions of mu by simply replacing this mu here by g of mu, or this mu here, I should say, by g of mu, and so forth. So all of a sudden I can find myself doing integrals with my samples, or approximating integrals, using my samples in a way that I could not previously do. And of course, I don't just need to limit myself to mu. I can do the same thing with tau, and I can even compute sort of averages over products and various functions of mu and tau if I choose to with my samples. So again, this is sort of a very specific application of Monte Carlo, and it's one where our samples are independent. Very shortly, we'll be sort of generalizing these arguments quite broadly and exploring Markov chain Monte Carlo. But for now, hopefully this makes sense, and talk to you shortly.